While every financial channel on this platform was busy screaming about IonQ and Rigetti and D-Wave and their wild stock price swings, a quiet research lab tucked into the hills near Malibu, California, just solved one of the single biggest engineering problems standing between quantum computing and reality, and almost nobody outside a small circle of physicists even noticed. No press conference with confetti, no breathless stock market headline, just a peer-reviewed paper published in one of the most respected scientific journals on the planet describing a quantum chip that, for the first time, essentially runs itself. Today we're going to break down exactly what this lab built, why it matters far more than another flashy stock, price headline, and why the fact that almost nobody is talking about it might actually be the most important detail in this entire story. Let's start with the basic problem this breakthrough actually solves, because understanding the problem is the only way TO understand why the solution is such a genuinely big deal. Every quantum computer that exists today, no matter which company built it, faces the exact same fundamental obstacle. The individual qubits, which are the basic building blocks of quantum information, are incredibly fragile and incredibly finicky. To keep them stable enough to do useful calculations, engineers have to cool them down to temperatures colder than deep space, just a fraction of a degree above absolute zero. And to control those qubits, to actually tell them what to do and read out what they're doing, engineers have traditionally needed massive racks of external electronics sitting outside the refrigerator, connected to the freezing cold chip through a tangle of wires running in and out of the cryogenic chamber. Here's why that wiring problem is such a massive roadblock to actually building a useful quantum computer. Today's experimental quantum chips might have somewhere between a few dozen and a few hundred qubits, but scientists generally agree that a truly useful, commercially transformative quantum computer, one capable of solving real-world problems in drug discovery, cryptography, and material science, will likely need thousands or even millions of qubits working together. Now, imagine trying to run a physical wire from an external control rack through the wall of a refrigerator down to each and every one of a million individual qubits. That is not just inconvenient. Many serious engineers consider it essentially physically impossible using the current approach. The wiring alone would introduce so much heat, so much electrical noise, and so much physical bulk that the entire system would become completely unworkable long before you ever got anywhere close to a million qubits. This is exactly the problem that a private research institution called HRL Laboratories just took a massive step toward solving. And the story of who HRL actually is deserves its own explanation, because it is not a household name the way IBM or Google is. HRL Laboratories is based in Malibu, California, and for decades it has operated as a kind of quiet, elite research powerhouse. Jointly owned by two industrial giants you would probably never associate with cutting-edge quantum physics, Boeing, and General Motors. Think about that ownership structure for a second. This is not a flashy Silicon Valley startup chasing headlines and venture capital. Hype cycles. This is a legacy research institution, historically focused on aerospace and defense-grade engineering, that has spent years quietly building some of the most sophisticated silicon-based quantum technology in the entire world, largely outside the spotlight that follows publicly traded quantum stocks. If you're finding this kind of deep, under-the-radar tech story valuable, go ahead and hit that subscribe button right now, because this is exactly the kind of overlooked breakthrough that most channels completely skip past in favor of chasing whatever stock is trending that week. So what did HRL actually publish, and what does it actually mean in plain language, without the dense technical jargon that usually keeps ordinary people from understanding why this news is so significant? In late July of this year, HRL Laboratories published a study in the scientific journal Nature, one of the most rigorously peer-reviewed and universally respected publications in all of science, describing what they called a silicon quantum processor that runs itself. Instead of relying on those massive external racks of room temperature controlled electronics we talked about earlier, HRL's engineers built a custom control chip using standard, commercially available semiconductor manufacturing technology, and placed that control chip directly inside the extreme cold environment right next to the qubits themselves. This custom chip, which the HRL team has nicknamed Sledge, operates at roughly 4 degrees above absolute zero, an environment so cold that most conventional electronics simply stop working properly or fail outright. Getting a chip built from standard, commercially manufacturable silicon germanium materials to reliably function at that temperature, generating every single control signal the qubits need without any help from room temperature equipment, is itself a remarkable engineering achievement that took years of dedicated research to accomplish. But here's the part that makes this breakthrough genuinely extraordinary rather than just incrementally interesting. This integrated system did not just sit there and passively hold its temperature. It actively and autonomously ran quantum error correction, which is widely considered one of the single most difficult and most essential routines that any future large-scale quantum computer will absolutely need to perform constantly and reliably in order to actually function as a useful machine. Quantum information is incredibly delicate, and tiny amounts of noise or interference can corrupt a calculation in fractions of a second. Error correction is the ongoing process of continuously checking for and fixing these tiny errors in real time, over and over again, thousands of times per second, for as long as the computer is running. Getting a fully self-contained system, sitting inside a refrigerator colder than outer space, to autonomously perform this incredibly delicate and complex error correction process with no real-time input needed from external room temperature electronics is precisely the kind of breakthrough that quantum computing researchers have been chasing for years. Before we go further, it's worth pausing to actually explain what a silicon spin qubit even is, because the term gets thrown around constantly in quantum computing coverage without ever being properly explained in plain language, and understanding it makes the rest of this story dramatically easier to follow. Traditional computer chips store information using electrical charge, essentially tiny switches that are either on or off, representing the ones and zeros that make up all digital computing. A silicon spin qubit, instead, stores quantum information using something called electron spin, which is a fundamental quantum mechanical property of a single electron trapped inside a tiny structure carved into silicon. Think of it loosely like a microscopic compass needle that can point in multiple directions simultaneously, thanks to the strange rules of quantum mechanics, rather than simply pointing one direction or the other, the way a classical switch would. The genuinely exciting part about building qubits this way is that the underlying physical structure looks remarkably similar to the transistors already used in ordinary computer. Chips, meaning the same general manufacturing techniques the semiconductor industry has spent 70 years perfecting, can, at least in theory, potentially be adapted to build these quantum devices as well. This stands in fairly sharp contrast to some of the other major approaches companies are pursuing in the broader quantum computing race. Google and IBM's existing flagship systems primarily rely on superconducting qubits, which are tiny loops of metal that have to be cooled to extreme temperatures and behave like artificial atoms when an electric current flows through them without any resistance. IonQ, meanwhile, uses trapped ion technology, suspending individual charged atoms in space using precisely tuned electromagnetic fields and controlling them with lasers. Each of these approaches has its own distinct advantages and disadvantages in terms of stability, error rates, and, critically, how difficult or how easy it eventually becomes to manufacture these systems at a massive commercial scale. Silicon spin qubits are often specifically highlighted by researchers as one of the more promising long-term paths toward manufacturability, precisely because they can potentially piggyback on decades of existing semiconductor fabrication infrastructure, rather than requiring an entirely new manufacturing ecosystem built completely from scratch. It's also worth taking a moment to properly explain quantum error correction itself, since we mentioned it as the core achievement here, but haven't yet unpacked exactly why it is so notoriously difficult. Classical computer chips already use basic error correction techniques, but the errors they're correcting for are relatively rare and relatively simple. Quantum systems are a completely different story. Individual qubits are so extraordinarily sensitive to their surrounding environment that even a tiny stray vibration, a minuscule fluctuation in temperature, or a slight amount of electromagnetic interference from a nearby wire can corrupt the fragile quantum state almost instantly. Because of this extreme fragility, useful quantum computers cannot simply rely on individual physical qubits being reliable on their own. Instead, engineers have to group multiple physical qubits together into what's called a logical qubit, using clever mathematical schemes to constantly monitor each other for errors and automatically correct them in real time, many thousands of times per second, without ever directly measuring or disturbing the actual fragile quantum information being processed, getting this entire delicate, continuously running correction process to happen autonomously, using a chip sitting directly inside the cryogenic environment itself, without needing constant guidance from external room temperature computers, is exactly the piece of the puzzle that has eluded researchers for years, and exactly the piece HRL's team just demonstrated working in a real physical device. Let's talk about the actual measured results, because the numbers behind this achievement are genuinely impressive and deserve to be understood clearly. The HRL team demonstrated an 18-qubit silicon spin processor integrated directly with their custom cryogenic control chip. Compared to previous demonstrations of this same general type of qubit technology, their new integrated system achieved control errors that were roughly 10 times lower than what had been shown before. On top of that, as they added more qubits into their error correcting scheme, known technically as a repetition code, the system showed approximately 5-fold error suppression, meaning the errors got meaningfully smaller and more manageable as the system scaled up rather than getting dramatically worse, which is exactly the kind of favorable scaling behavior that engineers desperately need to see if they ever hope to build a system with thousands or millions of qubits rather than just a few dozen. Now, why does this specific breakthrough matter so much more than it might initially sound like it does to someone hearing about it for the very first time? Because this is not just another headline about a slightly bigger or slightly faster quantum chip. This is a breakthrough in the underlying manufacturing and engineering architecture that could plausibly determine whether quantum computers can ever actually be scaled up to a useful size at all. Building a bigger quantum chip is one challenge. Building the surrounding infrastructure that can actually control, monitor, and correct errors on that chip once it gets large enough to be genuinely useful is, in many ways, an even harder and more fundamental challenge. And D, it is a challenge that has received far less mainstream media attention specifically because it is less visually dramatic and far more difficult to explain in a short, punchy headline. Compare this to the kind of quantum computing news that typically dominates financial media and social media feeds. When Google announced its Willow chip breakthrough, headlines exploded because the story came with a wildly dramatic, easy-to-understand comparison, claiming the chip performed a calculation in minutes that would take today's fastest supercomputers longer than the entire age of the universe to complete. That is an incredibly compelling, headline-friendly claim. HRL's breakthrough, by contrast, is about something far less flashy on the surface, the boring but absolutely essential plumbing and infrastructure required to eventually make quantum computers work reliably at meaningful scale. It does not come with an easy, viral, jaw-dropping soundbite, but in terms of actual practical importance to the long-term trajectory of the entire industry, many serious quantum physicists and engineers would argue that solving the control and error correction infrastructure problem is every bit as important, and arguably even more important in the near term, than any single flashy computational benchmark demonstration. This is exactly why this story has largely flown under the radar, while speculative quantum stocks continue dominating financial headlines and investing content across every platform. Solving a foundational engineering bottleneck simply does not generate the same kind of viral excitement as a chart, showing a stock price going up 400% in a single year.